Hi, it's Clark on Temptress. Today I'm going to do probably the most important electrical video I've ever done. I'm going to teach you a secret for solving probably the hardest problem that you could have in a live power system. Over a year ago, I started this series on, I think I call it the Master Class of Electrical or something on that order. I'll put a card up now and the link in the description for the playlist that is the whole thing. This is going to be the lowest video, well, the last video in that playlist. You really need to watch a lot of the videos in the playlist. I know I put a few in there that might have had to do with batteries or BankManager. You can skip those, but you need to know Ohm's law. You need to know how resistance in wires works. You need to know how to use a meter, and it's all in that series. Given all that, today we're going to talk about one of my secrets, I guess. I don't know secret is the word. I mean, I just have never seen anybody else use this method. I gave a seminar on the beach in Georgetown many years ago where I went through all this with a demonstration and batteries and fans and things, and nobody said, oh yeah, I do that all the time. But I did hear a lot of people saying, oh dude, Clark, I mean, I had this problem and I just couldn't solve it. It's been bothering me for a while, and it's solved. I found it. There was some resistance in my circuit somewhere. That's what it always is, especially on boats. You could have two perfectly good looking wires with two perfectly clean looking terminals bolted together by a big bronze bolt, and there can be resistance, even though you can't see it. In this video, we're going to learn how to see it, how to know exactly where the resistance is in the circuit, how to find it, how to know whether it's worth digging into that cupboard to check something or not. And the or not will save you so much frustration. This will let you pinpoint where the problem is in your circuit. Now, electrical problems, I guess, can be broken down into two categories. You turn on the switch and nothing happens. You turn on the switch and it doesn't work right. Now that first method, it's actually pretty simple, because you turn the switch and nothing happens. You just take your meter back until you find 12 volts, let's say, and then where you don't find it, well, that's the problem. The problem is the other one. It shows its head in lots of ways, usually in higher current devices, but it can show itself anywhere. It can be a fan that just doesn't spin fast enough. It can be a light that flickers or doesn't come on as bright as you remember. It can particularly be your engine won't start. You push the button and you just get clickety-click, but you don't get the engine to start. Now, in the case of the engine, always first take your meter, go back to the battery, and make sure the battery's not just discharged, because that's the easy fix. But very often, the battery will be charged right up, 12.8, and you push the button and you get nothing. Or you get nothing some days, and some days it starts. We're going to go into why that is and precisely how to find the fault. The fault is usually caused by corrosion that has happened in the electrical system someplace. For those of us that live on boats, we're in a saltwater environment. Copper loves to react in a saltwater environment and make this corroded mess. Sometimes it can be a corroded mess that doesn't even look bad. Sometimes it can be a bad crimp, and it's always been a problem, but because of another problem of a weakening condition somewhere else, it has just gone below the line of functioning, and now it's the biggest problem. To look into this, we have to start with a little bit of math. This is the math I do in the very first video. Won't go into it deep here. I'm going to assume you have a working knowledge of Ohm's law, but we only need a bit of it. Ohm's law, you know, volts equals amps times resistance. Every circuit in the world uses this. Now, every conductor has resistance, as I talked about. Every terminal connection has a little more resistance. Every screw-down connection where they hook together has resistance. There's resistance everywhere. As long as that resistance is itty-bitty, it's not too much of a problem. But if it grows, it will cause what we call a voltage drop. And you can use Ohm's law to calculate that. If you know the amps that are going through the circuit, and you know the resistance in an area, well, you could calculate over that area how much voltage drop there will be. Voltage drop is just that, a drop in voltage. If you had a battery that was putting out 12.8 and you checked it and it's 12.8, great, but circuit's running, and then you go to the other end of the circuit and it says 8 volts. What the heck? Well, we do know that the device at the other end is only getting 8 volts, and if it's operating, it's actually has its own 8-volt voltage drop right there. But that's kind of how it works. It should have that. But we've got those other, 2.8 volts that we've got to account for somewhere. This is going to be the method. I probably could go on with theory quite a bit before I dive into it. But I'm going to try it this way. I'm going to actually set up a little lab on my workbench here. And I'm going to set up a circuit with a resistance in it so we can measure the voltage drop and we can figure out and see what's happening. So what we're going to do is build your common boat type system. Except I'm not going to use boat components. I could use a battery. I've got batteries here. I could use loads like fans and maybe an inverter with a load on it. But the problem is all of those things aren't fixed. The more power I take from a battery, the lower its voltage goes. And I would like this ideal battery that just stays at whatever voltage I tell it no matter what. It can like self-adjust itself. For that, I'm going to use this. This is my bench power supply, and it's just that. I can turn it on. I can tell it how many volts, and I can adjust it that it should be putting out. For this, we'll set it for, let's say 14 volts. Little fiddly because it's cheap Chinese. So that's going to stay at 14 volts if it possibly can. This other one down here, I can adjust the maximum amps it puts out. It's going to actually display the amps that it's currently putting out, which is 0 because, well, circuit's open. But I can adjust that. I've got it cranked all the way up. For the purpose of this, I just want as much power as I'm asking for, but keep the 14 volts. This guy can only put out 5 volts, so we don't have to worry about that. So cranked all the way up is 5. Now for my load, I'm going to use this. This is a device I use when I do the battery analysis, and it's a calibrated load. I can tell it how many amps to draw, and it will draw that number of amps. Even if the voltage changes, it'll keep it there. A real load, as the voltage goes down, they tend to drop in amperage. Motors under a load, like the starter in your boat, the exact opposite. As the voltage goes down, it wants a certain number of watts to do the work you're asking, so it will actually go up in amps. Either way, we don't want things changing, so we're going to use this. Plug this in. Okay, let's hook it up. Start out with, we'll take this wire and hook it to the positive load terminal. Nice, good connection, and this is a good wire. And we'll hook this to the positive coming from the power supply. We'll take the ground wire, we'll hook it to the negative load terminal. And bang, this thing jumped right to 14 volts. So this is giving out 14 volts. There's virtually no voltage drop, and this says, I'm seeing 14 volts. This is what we would expect. Now I'm going to turn up the amp draw. I'm going to actually make this thing consume power. So turn this knob up. Let's set it for 4 amps. It's a little fiddly, but there we go. 401. 4, okay. At 4 amps, there's 13.5 volts that get to here. This is still putting out 14, but this is 13.5. So we have a half a volt of drop in these wires and this connection. Half a volt, not so bad. It's 12 volts total, so, you know, it's a reasonable percentage. The problem with running a system on 12 volts is little bits of voltage drop make a huge amount of a problem because we only have the 12 to start with. If we had 120 volts, losing a half a volt, we wouldn't even notice it. The other thing is, for the amount of power we push, we have to push 10 times as many amps because remember, power is watts, back to the old videos, and if at 12 volts we push 10 amps, that's 120 watts. At 120 volts, like your AC in your house, 120 times 1 amp is 120 watts. So as you can see, we have to move a lot more power in a lower voltage system, a lot more current, a lot more amps in a lower voltage system. The more amps we move, the bigger the voltage drop's going to be, hence the bigger the problem. So at 12 volts, we're always fighting that. That's why our wires are so big. That's why corrosion is such an issue. But let's continue with this a bit. So 4 amps, 13.5 volts with 14 volts being delivered. This is a 1/2 ohm resistor. Its whole purpose in life is to cause resistance. If I run this circuit through this component, there will be a voltage drop caused by an extra 1/2 ohm of resistance. We can calculate that because Ohm's law, right? So the voltage drop will be 4 amps times 0.5 ohms. So it should be 2 volts of drop. Let's take a look at that. Open the circuit. Of course, everything stops. Clip it in here. And what do we see? We are now at 11.5 volts. Remember, we were 13.5, so we lost 2 more volts across this. Let's come into how you would do this on a boat now. Here's my meter. I'm going to set that for voltage. Doing this particular study, I got to keep an eye on this because it's actually making power and it's going to get hot. It's okay now. Doing this particular study, you need a multimeter, a voltmeter, and it doesn't have to be a super high-end one. This is my lab bench, and it's a pretty good meter. I haven't calibrated it in a while, but it's pretty good. If all you had was like a crazy, stupid, well, don't go as slow as like a Harbor Freight meter, but if you had a meter that was always off by a little bit, as long as you do all of this test, every single part of it with the same meter, it will be off the same everywhere, and it'll still guide you through solving the problem. What you don't want to do is count on this meter, and this meter, because they don't necessarily calibrate with each other. They will here because they're all good meters. But just don't do that. Don't use that wall meter on the wall to say that's the battery voltage, because it isn't. First off, it's the voltage someplace else in your system, and second off, it's a different meter. None of them are to be trusted. Those of you that come to me with problems with your BankManager and we're trying to work out the installation, what is one of the first things I always say? Only give me the numbers the BankManager gives you. Don't give me numbers from other devices. That's because we need to have them all calibrated to each other. If we use the same meter, they're calibrated to each other. Okay, so let's do this now. So I got my meter. Let's start at this end. Is this getting hot yet? It's okay. So I touch these two, and what do I get? 11.435. It's pretty darn close. Oh, 11.43. We're getting what we're getting. We go back to here, and I get, whoops, I'm holding the pins backwards. If you hold the pins backwards, it doesn't matter. You'll just get a negative sign, but it should be exactly the same reading. My power supply says 14 volts, but my meter says 13.86, almost 13.9. That makes sense because this is actually measuring the voltage inside the device. And there's a lot of voltage drop in these connectors and the wires that come to these connectors, and that would be about the right amount. Here's the important part though. We want to find this. Like, we don't know where it is, and we're just trying to discover it now. We see we have a problem, and now we'd like to discover it. Well, first thing we can do is you get a really long wire and get yourself some kind of way to clip it onto your meter in a good way. Alligator clips are great, but have a long wire. Doesn't matter how big that wire is because we're only running signal through it, no current. So it could be tiny gauge. Hold it on, or have your wife or whatever, hold it on to the negative of the battery and take it to the negative of the load when the load is running, you know. And what do we get here? We get 0.11 volts. Well, we're searching for like 2 volts. 0.11 is a thing. We should write that down. Get my pen here. So we know we're losing 3.6 volts. And on the negative side, on the main lug, we went down. Check it again. 0.11 volts. Now let's go right to the positive side. It doesn't really matter if we read backwards, so I'm just not going to switch hands. I put the negative there and the positive over here. And look at that. 2.35 volts on the positive side. That says, hey, look, 2.3 volts of the drop is on the positive side of the track. Only 0.11 volts is on the negative side. We're going to do further investigation on the positive side. Let's say this was a switch or a fuse or your bus bar. It doesn't matter. It's something along the way. So the next step, we take our meter and we put it between the load and that thing. And that tells us 0.08. Yeah, that's almost nothing. But on the next test, we write down 0.08. We might have checked this first. So we go from the battery to that device. And we found 0.099. So let's say 0.1. Well, if we go right to this itself, what do we find? Across this, we have basically 2.2 volts of drop across the device. If we add these up, remember we have 2.35 somewhere in there. 2.2 becomes 2.38. There's our total voltage drop on the positive side. And we know the problem is here. So in the case of your boat, most likely you would take this apart. You would maybe clean up the contacts. You would take a look at the device and say, hey, what should I do here? If it was a power bus, just clean, because it's just a piece of copper. Nothing wrong with that. If it's a switch and it has a lot of voltage drop in it, get a new switch. And getting a new switch would be bypassing the problem, right? If we do that same test now that we've removed that, the negative side should still give us 0.11, yep. And the positive side will give us 0.18. Well, reasonable numbers. What's our total? 13.5. Back to where we were. That's the heart of it. That's how you would find problems. Now, there might be 27 connectors on the way, but you start with the ones that are easy to get to. Probably the battery and the load. Do the negative side, do the positive side. It's just as likely to be the negative side. And usually the common wisdom is check the negative first. For whatever reason, people always think it's the negative. For the engine, it very often is the negative side. Check the negative, check the positive. Decide, oh, my problem's in the positive. Then just start breaking it in half. Go from one end to where it's convenient. Do the most convenient parts first. And eventually you might find that, oh, there's this wire going into this cabinet that's miserable to get to. And it comes out again. And I found there's like 2 volts of drop in this cabinet. Well, you got to go in that cabinet. But if you did the same test and you find there's no voltage drop in the cabinet, there's no need to open it up. Doesn't matter what's happening in there. There's no voltage drop. There's no resistance. It's fine. I'm going to turn this off now. I do wish I had some better props here. On the boat, I have no shortage of big, corroded, ugly terminal wires. So you're going to have to use your imagination a little bit. But this works for all size wires, so this is valid. Here's a piece of wire with 2 very nicely attached crimp connectors. They have shrink wrap type plastic on them that's glued right into the plastic. Very little ability for water, moisture to get in here and cause a problem. But, you know, anything could happen. Let's say we needed to connect this to something else and we did it this way. And we had it on some kind of a bus bar. And it both bolted onto the same lug of the bus bar. What would we check? We found that the problem is in this area. So what should we check? Well, we should check the whole wire, of course, from the most convenient to the most convenient. And let's say, oh, yeah, it's this wire. And you look at it and go, it's this wire. I'm going from metal on one end to metal on the other side, and I'm seeing voltage drop, but it looks beautiful. Well, you got to go further. A very big cause of voltage drop is the actual crimp connector, in which case it's worth it because you have to find the problem anyway, to stab it. Ouch, these are sharp. Stab it right in so you make contact with the copper with one of your probes, or use something else. If you want to, you could stick a sewing needle in. I do that a lot. It's metal, so you can make a contact there and there. And if you find that you're having a bunch of voltage drop, well, there's your problem. Easy, cut it off, put a new one on, you're probably good. Let's say you had a couple of these stacked up, and you actually, and I've seen this happen, you think it's impossible. You have these together, they're bolted down, and you checked from this terminal to this terminal, and they're touching each other, and they're clean, and there's your voltage drop. Well, take them apart and make them really clean, sand them down, put them back together, and that'll be better. It's kind of nice when you put things like this together, if you don't want the problem to happen again, to put something on it that keeps the air and moisture away. There's a lot of said chemicals around. For big things like this that only have one circuit, I like to use conductive grease. Greases that are loaded with either carbon or copper, and that works pretty good. The conductive helps a bit, but the grease helps a lot. It keeps the moisture and the oxygen in such a way. If you're going to do it on a plug that has like 10 different, you can't use conductive grease because it'll jump and screw up the circuit. So they make something called dielectric grease. Dielectric just means it's not conductive. So you put some of that in and shove it in, and the metal to metal pushes the grease out of the way and makes a perfectly good contact, but the grease ends up surrounding it. So that's good. What else can we learn from all of this that might help us find it? Well, this is still quite warm because it's been putting out, 2 volts drop, 4 amps. So it's been putting out 8 watts for quite a while, and it got warm. It would have continued to get warm. I guess it was dissipating at the rate it was making power. That means we can use that to our advantage. A little bit of temperature rise is a good indicator there's heat happening. Touch it, but it's hard because only a little bit, you might not feel it. But if you do get a thermal camera, and they're getting cheap enough that's not ridiculous. Like I have this little thermal camera that I just plug into my cell phone. I use for everything. You can just look at all the circuitry, and just a couple degrees of temperature will show up on that. And it'll be like glowing white compared to everything else. Well, what's easier than being able to have like superhuman electrical abilities and look into a wire cabinet and say, well, there's your problem right there, because it's the hot spot. All right, I think that's about it. I hope this is useful to you. Definitely think about this particular method. If you don't have a use for it right away, bookmark it. It might sound like something you'll never use right now, but I swear to you, you will never use it until you know it, and the first time you use it because you actually have a problem, well, you'll never want to be without it again. It is really useful. I'd like everybody to know about this. This is one of my better ideas, I think. This is up there with how to fix a dinghy cheaply. This whole playlist I would like shared. I say that at the beginning, and you guys did, and I really thank you. It got a lot more views than I thought. I thought talking about this kind of esoteric electrical stuff was just going to go over most people's heads, and nobody was going to watch this series. Well, it's become a very popular series. So wherever you shared it before, please share it again. Whatever forums you hang out in, please do. Everybody's a favor. If you like this set of videos, share it. Let's get this out, and let's make it so people can solve their own electrical problems on their boats. Bye from Clark on Temptress, and I hope this is useful.